In this unit, we're going to discuss application security controls. So applications are an attack vector, just like any other attack vector we've discussed throughout the semester. But in this unit, we're going to discuss specifically with applications how they can be attacked and how we can protect ourselves or mitigate those risks of attack against specific applications, or specifically applications, I should say. The first thing that we discuss as far as securing applications is secure coding concepts. And basically the idea here is testing. But your book talks about how vulnerabilities in software represent a common attack vector. In fact, I think that's probably one of the most common attack vectors, vulnerabilities in software, because we have lots of vulnerabilities that attackers can take advantage of. And you got to remember that almost everything in IT is software, right? So there's always things like buffer overflows and cross-site scripting, all the things that we've talked about throughout the semester, we can try to protect against in our applications. In your book, they talk about the software development lifecycle, the SDLC, and this is basically how people develop or how companies develop software. And there's 4 basic steps that you need to be aware of for this course, and that is the analysis phase, which is all about understanding the problem domain or understanding what we're trying to design for, or the problem that we're trying to fix, or the problem that we're trying to address by designing some software. And then there's the design phase where we're taking that understanding of the problem and trying to design software to solve that problem. And then the implementation, which is when we actually code that system. So we're actually developing that system, or we're installing, we're configuring, we're setting up hosts, we're setting up servers, all that stuff for implementation, for actually putting that system online. Once we've got all that stuff done, we're going to have to do some testing. So we have to do lots of testing to make sure that we don't have all these flaws that we talked about. And testing is not easy to do. I think a lot of people underestimate testing, and it takes certainly a lot of skill and almost an art to do good testing. And they're kind of unsung heroes in software development. Where I work, we have a testing department, and when things go well, we almost always forget about testing. But when something goes bad, when software gets released and there's some major flaw, people come back to QA and say, well, gee, how come you guys didn't catch this? And they say, well, what about these other 5,000 issues that we did catch that were, if not as serious, maybe perhaps more serious? So a lot of times, one little thing slips through and there's a lot of scrutiny on people who do testing. So it's certainly not easy, and it takes a lot of skill to understand how to effectively test software to make sure we catch a lot of these vulnerabilities that attackers would take advantage of in the field once software gets released. So the mitigation techniques that we're going to talk about, number 1 is input validation. So how we can test and see how the software handles, or how the program handles invalid input. So if somebody puts in, either purposefully or non-purposefully, somebody puts in some malformed input, is it going to handle it? Is it going to blow up? Is it going to give you a list of all the users? A lot of the things that we talked about previously with injection attacks, these various injection attacks that we discussed. You can also look at error and exception handling, which we're going to talk about in just another slide. Cross-site scripting, which again we've already talked about previously, but we'll talk about some techniques that you can use for testing for that. And obviously there's some additional testing that you can do. And then application hardening we'll talk about. So we'll talk about how to actually, the steps that you can take to try to harden applications against attack once you have them implemented, once they're in the field. So first, error and exception handling. So vulnerabilities, as I said before, represent the most common attack vector. And one of those is error handling. So errors can expose useful information to attackers. So they got to be handled, or they have to be trapped in a certain way that attackers can't see that information. And you might be asking yourself, well, what kinds of information might errors expose? Well, if you're planning a SQL injection attack, when you type in to your web browser, the beginnings of your SQL injection, a lot of times what an attacker is looking for is a response that gives them some clue as to the schema of the database. So, one thing that'd be very useful for an attacker trying a SQL injection attack is to know the name of a table or the name of the fields. So if the error comes back and says user underscore last name, comma, user underscore first name not found, or something like that, then the attacker might say, aha, the column names are user underscore this and user underscore that, and they might be able to extrapolate that from some additional information. So you do want to make sure that that type of information is not displayed to a user. It should be more generic. It should be very vague, and it should be, not vague to the point of something went wrong, have a nice day, One of the things that always bothers me when I use applications is it'll just say error found, contact your system administrator, right? Well, what do you tell the system administrator? What was the error you got? I don't know. It just said to call you. So, you do want to have some exact wording in there, but you don't want to expose any of the internal workings of the system in those error messages. Your book also discusses log files. And log files can expose a lot of important information or a lot of protected information. So log files are very useful. I don't want to downplay log files. Log files are great, and they really allow us to figure out what's happening in some application or software when things go wrong, and it's very helpful to have them. However, if the log files fall into the wrong hands, again, they're going to get a lot of insight into how the system works. They're going to understand a lot of the architecture. And I do this all the time. So in my job, I will have customers sometimes that will send me log files to other vendors' software. And a lot of times I can use those log files to figure out a lot of things about their software. Sometimes I can even identify what libraries they're using because of the vernacular in the log files. Just something over time and with experience to start to get the hang of that stuff. So it's amazing the information that you can glean off of log files, even when you think there's not a lot of stuff in there. So they have to be protected. You want to password protect them, encrypt them, whatever you have to do to make sure that attackers can't get their hands on the log files. And like I said before, don't display detailed errors to users unless you're in debug mode. So, and your book talks about this very briefly, but sometimes when we're implementing software for a period of time, when we're testing and things like that, we'll put the software in some kind of debug mode so that we don't have to go digging through log files to find out what went wrong. Instead, we can just see it right in the application. It makes things a lot easier. So certainly most applications support debug mode, but what would be dangerous is to leave an application in debug mode when it goes into production. So then all of your users are seeing those debug messages. We certainly don't want to do that. In your book, they discuss error handling, and I don't recall if they specifically talk about how error handling is done in applications, but generally there are two methods to do error handling, or two methods that we typically see in applications for error handling. And the first one is function-based, which is where basically we just try to catch the errors in our software. So maybe through some conditional statements or, and so forth and so on, we try to catch errors and just display them or throw them out to a log file somewhere. And function-based error logging can be rather confusing because it's the programmers kind of doing this on their own, and it's not really clear that they're catching errors when you look at the program code or the source code. But it's very easy to write in this type of error logging. The other problem with function-based is it doesn't always catch every single error. So you're basically with function-based, you're checking for a specific condition, and then you're doing something. So for example, with input validation, you might test the condition that there's a single quote somewhere in the input. And if there is, you're going to do some kind of an error thing and you're going to log it out. But that only catches the single quote. What if it's something else? It might not catch that, and so forth and so on. So function-based error handling is effective, but not completely effective. The other method is structured, which is the try-catch method. This is where you wrap each section of your code with a try, which means try this block of code, and if that block of code fails, catch it and do something. And usually that catch is to do something alternative or to put some error logging somewhere, and or both. And this would be the preferred method for error handling in most applications. And a lot of times you'll have a combination of both. So sometimes you'll have some specific conditions that you're checking for with certain error handling, but then you're wrapping all of that stuff with the try-catch methods. So that's certainly one way. And one thing that error handling with the try-catch method, by the way, don't get confused by the term structure. There's two types of programming that we talk about in most CS programs, and in this program specifically we talk about structured programming and object-oriented programming. Structured try-catch is something that can be in both structured and object-oriented. So don't get that term too confused with, the vernacular kind of crosses over both areas. But a structured error handling is using try-catches in your code, which again is the preferred method. And because that catch can do something alternative when an error condition happens, you can tell the program to do something specific. Your book talks about this idea of fail-safe, which is when your program is going to fail, you want to make sure that it fails into a condition or into a state that is safe, that is not just sitting out there waiting for something to happen. So you want to make sure that your program goes unambiguously into some other condition so that an attacker can't take advantage of it. And one thing you can think of, for as far as fail safe is, what if the program is in the middle of doing something with the data? The data could be in transit. The data could be ephemeral data. By the way, ephemeral data is a fancy way of saying data in memory, right? So that's data that it's using. Data that's in the future is going to be output somewhere, basically, is ephemeral data. Same with data in transit. It's data that's being moved around. And that doesn't necessarily mean in transit through a network. A lot of complex applications are moving data between different packages and different services and so forth and so on. There's things like APIs and remote procedure call, or RPC. You've got Microsoft message queuing and things like that. All of those different mechanisms have holes that attackers can take advantage of. So if a program goes into some state where that data is just sitting out there in, say, a message queue in Microsoft or an RPC, it could be gleaned by an attacker and they could use that data. Same with the ephemeral data. It could be sitting in memory and so forth and so on. So we want to make sure that when that catch happens, that we're doing something safe, that we're bringing the application into some kind of a fail safe. So that's another possibility. There's also this idea of noise, that attackers can use noise to kind of confuse you when you're trying to detect that attackers are trying to attack an application. So they can generate benign log entries so that their log entry is not as noticeable when they're trying to do something bad. So that's the idea behind noise. I don't know if your book really discusses noise in much detail, but I wanted to mention it here because it is an important concept. So input validation, we already talked about SQL injection. We talked about cross-site scripting. We talked about path traversal, which is where we might be able to, get ourselves into other paths using the the trust of the application that we're using. We talked about, we haven't really talked about canonicalization attacks, but this is basically using various encoding to inject malicious data. You can take a look at RFC 2279 to see all these different types of encodings to understand what I'm talking about with encoding, but I'll summarize it here for you. Encoding is basically, you've got ASCII, you've got UTF-8, you've got ANSI encodings, all these different ways of representing characters with the bytes and the bits that underlie them. And ASCII, of course, is one of the most common. UTF-8 uses ASCII, but also can support other languages and other characters, so it's kind of extends beyond ASCII. So one of canonicalization attacks are becoming more common, where attackers are figuring out ways of injecting code by using encoding. So in other words, if there are bytes that are unused in the encoding, you can sneak your code into these little empty areas, areas you wouldn't normally use. So you can use other encoding mechanisms when you submit your data to, say, a web server. And if that web server doesn't understand that encoding, it's going to take that data and just put it somewhere, and that could be malicious code. And there are certainly some examples in the wild of that happening. So canonicalization is certainly an interesting attack, which our book I don't think talks about in too much detail, but it's certainly something you could take a look at and look into. So the point of all this is that you want to consider all input to your application to be hostile. You can't trust anyone. And I've worked with people in the past where they say, well, once somebody logs into the system, they're a trusted user, so I don't have to do input validation because I can trust that user. And that's kind of flawed thinking, because you always have to assume that somebody could get to that form or get to that input somehow and have taken advantage of some trust somewhere downstream. So always assume that you can't trust the input. It's always a good stance to take when you're doing input validation and when you're testing for input validation. We'll talk more in another slide about some methods to test input validation. So you want to sanitize all input. You want to verify the encoding, which would protect against the canonicalization attacks I just talked about. Sanitizing input would help protect us against SQL injection, cross-site scripting, path traversal, right? So we can strip out any of those special all that special stuff that that we don't want to make it into our application. So all those illegal characters we can get rid of, and we can whitelist acceptable values. So we can say so for example, if you have a form or if you have input that's asking for a state that somebody lives in, you can whitelist acceptable values for state. That's one less avenue of attack, because no matter what, it has to be a valid state. And it makes sense because you would probably want that anyway. You would want to make sure people are putting in a valid value for something like state. You could do the same thing with something like a zip code, for example. If you're asking for a zip code, you should not be getting letters in a zip code field, at least not in the United States. And again, if you're looking at other countries, there are other formats, but you could restrict input to comply with those patterns. And you can do some pattern recognition to make sure that those inputs comply with those patterns before you move on and do anything with that input. So you can use whitelisting as just another technique. So fuzz testing is kind of a newer technique. I think it's been around since the late 80s, early 90s perhaps. We started seeing this idea of fuzz testing come on the scene. But the basic idea here is that we don't know what we don't know. In other words, when you're doing testing, it's almost impossible to test for every possible scenario for these various injection attacks. It's hard to understand exactly how your application is going to react to different types of input. So fuzzing is this idea that you can systematically provide random data as input to your system. So you can have some program that programmatically is trying different things against your application to see if anything fails. So as you're sending this random data to your application, any exceptions or crashes could then be analyzed against the random data that was passed, so you can see what in that random data would have caused that crash or exception, and that would expose flaws in how you're handling those inputs. So it can be effective for detecting things like memory leaks, buffer overflow errors, so that random data could cause buffer overflow errors, and all these other things that we talked about. I would say it's not very effective for things like SQL injection or cross-site scripting. For those types of attacks, we kind of know what the pattern of that data is going to look like, and we can test for those things. This is really for testing the unknown stuff that's going to cause these more insidious things like the buffer overflow and the memory leaks and so forth and so on. So, and even canonicalization attacks you could detect with these random, the random data that's getting passed, or random binary data. So again, fuzzing is kind of a newer technique, but it's becoming more popular. And if you look online at things like OWASP, they'll talk about fuzzing as a technique. In fact, they actually give you some very specific guidelines about how to do fuzzing against web-based applications that are SOAP or service-oriented architecture, RESTful or representational state transfer, which is another type of web service, and APIs and things like that. So they give you a lot of good advice and a lot of good guidelines for doing that type of testing on OWASP. Cross-site scripting prevention. So, and we've talked about cross-site scripting. If you recall, there were three types of cross-site scripting. There was non-persistent, persistent, and DOM-based. And I don't think we talked about DOM-based too much, but I'll explain just a little bit here just to refresh your memory. Non-persistent was it was when you injected some code through input that would only affect the web page that you're looking at, that you can see in your session. Whereas persistent would affect everyone. So everybody who would go to that website would see that injected attack. So I gave you two examples of that. I showed you one where we were able to hijack a search screen, and we could, in theory, use the URL for that search screen to send that URL to other people, so you could kind of see how that non-persistent attack could still be useful. We talked about a persistent attack. I showed you an example of doing that with like a Facebook kind of thing, where the user submits some input, but that input is cached for other people to see, so that flaw or that attack would permeate to anyone who goes to that page and sees their little comment thread or something like that. And DOM-based, so the DOM is the document object model, which is used by web browsers for JavaScript, and it's how you can control things in a web page. That's kind of a very simplistic explanation of it. If you take a JavaScript class, then you would obviously learn a whole lot about the DOM. But you can take advantage of the DOM with JavaScript, with cross-site scripting, just like you can with anything else. So that's why I think it's mentioned in this unit. So cross-site scripting attacks can involve theft of authentication information, session hijacking, deploying hostile content, changing settings in browsers and things like that, or in applications. It could be phishing, trying to get information from people, or spawning all these emails that go out to people and things like that. So we can protect using, and probably the most effective way to protect against cross-site scripting is to implement libraries that protect against cross-site scripting. So just about every programming language for the web has libraries. So if you're using PHP or Python, or even the more obscure ones like Perl or Ruby or something like that, or ASP.NET, is obviously a very popular language, and certainly PHP and ASP.NET there's no shortage of libraries that can help you protect against the cross-site scripting. So that's certainly one great way. The work's already been done for you. All you have to do is implement those libraries. There's really no excuse not to do that. So that's certainly one example. You can limit the types and sizes of inputs and uploaded files. So if you put these limiting factors, and I talked a little bit about this before with our input validation, we can sort of whitelist what's allowed, and that drastically reduces that the attack surface on our applications by doing that. All right, so let's go to the next little section here from our book. It talks about cross-site request forgery, which is very similar to cross-site scripting. And this one's a little different. We didn't really talk about this previously, but it exploits a site's trust with authenticated users. So in your book, there's an example of a bank transaction where a user logs into their bank on one tab in something like Chrome or Firefox or something like that. And then maybe they open up another tab and go to a different website. Well, that other website might be able to take advantage of the cookie that has their authentication token cached to do a transaction on the user's behalf. So it's this idea of transitive trust, which of course we've talked about before and we'll talk about again, where the trust to the browser, which is a transitive trust relationship, we can take advantage of that from another tab in the browser by hijacking that cookie and using that session. So your book talks about some mitigation techniques for that. One is you can limit authentication times. So for example, once a user authenticates, and I think all of us have seen this with our banks, when I log into my bank, they're very careful about making sure that if I don't do anything in my browser for it seems like just a few minutes, I get logged off the bank's website. So they limit the amount of time that you've got a valid authentication. They expire the cookies so they can't be hijacked later on. They do header checking is another method. I don't want to get too much into HTTP headers, but this is you can check the header against previous authentication attempts and make sure everything is copacetic. And the other one is random tokens in form submissions. So every time somebody submits information or tries to do something, you can have random tokens that are further authenticating that session. So a couple different mitigation techniques for cross-site request forgery, which I don't think is very common, but your book does talk about that there are some examples out in the wild, but certainly anything that somebody could take advantage of, we'd want to protect ourselves against. In the next part of the book, they go into application hardening. And so the rest of this chapter in the book is about application hardening. And the first, when we talk about application hardening, so if you recall, we talked about system hardening from previous units. And we can take those same principles to harden our application. So the same basic idea. So for example, removing unnecessary components, ensuring the proper configuration settings, making sure you've got all your updates and patches, all that stuff that we talked about at the, in all of our IT infrastructure, we can do on sort of a micro scale at our application layer to harden our applications as well. So as far as baselining goes, and we've talked about baselining before, so the proper settings and configurations for an application are basically determined using the same principles that we use to harden our servers. So when we did server hardening, we could do the same thing for application hardening, but we're going to basically set up the application. So here's some techniques. We're basically going to set up the application, and we're going to set all of its security settings. We're going to set up all of its access control, and we're going to document everything that we've done and make sure that every time that application is deployed, it complies with the baseline. So that's option number one. And we talked about, from a server level, if we're doing server hardening or workstation hardening, and we'll talk more about host-based security in the next unit, but for server hardening, we talked about removing all of those unneeded components, verifying the configurations, getting everything to where it's secure for your environment. And we can do the same thing with our applications. We can make sure they're secure for our environment. And of course, we want to make sure that everything is patched. So we always want to make sure we're running the most secure and recent version of an application. Those are typically going to be the most protected against attack. If there's a 0-day vulnerability, obviously at some point you're going to have a patch that's going to fix that, or hopefully would have a patch that's going to fix that. So we always want to get those installed in a timely manner. So you should have a formal process that's established to ensure that application layer patches are being applied. And a lot of organizations miss this. So, I think just about everyone or most organizations are able to apply some kind of patch management for the operating system level for both Unix, Linux, and Windows, of course, and even Mac. And that's not hard to do because everything is going to run one of those 2 or 3 operating systems. So they're pretty common, and you can come up with one policy for all that stuff as a blanket policy. The problem with applications is we've got lots of different applications on our network. In some organizations, thousands of different applications that have to get managed. Most of my customers that I work with have thousands upon thousands of applications, and all of them have their own sets of patches and their own sets of configuration settings and all that stuff. But you want to make sure you have some method to make sure that those applications are patched. And there's lots of techniques to do that. Your book doesn't really talk about in detail any good techniques for that, but it definitely is a challenge because of how distributed that challenge is. Because you've got all these different vendors running different software that is patched in different ways, and they have different ways of informing you that patches are available. So, for example, some companies will automatically tell you that there's a patch available in the software during each runtime. So if you restart a service or if you run an application, it'll warn you and say you're on version 4.3, but 4.4 is available. Would you like to upgrade? Other vendors will simply send an email or put a posting on their website. And some vendors won't tell you at all. They don't tell you that there's a patch until you call because there's something wrong. They say, hey, we're having this issue, and the vendor says, oh, yeah, well, we've got a patch to fix that issue. So that can certainly be frustrating. So lots of different methods of getting these patches, but you want to make sure you've got some policies and procedures in place to ensure that you've got some patch management for applications and understand how important it is to keep those applications on the latest versions. In your book, they talk about NoSQL versus SQL, and it kind of feels out of place when you look at this in the book when they discuss NoSQL versus SQL. So what is this? What are they talking about? They're talking about relational versus non-relational databases. So what is a relational database? A relational database is a database that enforces referential integrity. In other words, take a system or a database that tracks classes. So you guys are enrolled in a class right now at a university or a college, and that class has students. And the idea in referential integrity is I should not be able to delete a class that contains students. I have to get rid of all the students from that class first before I can remove the course. And I wouldn't want to be able to remove, say for a student, let's say a student has an email address. I shouldn't be able to remove the student until I've removed their email address first. Otherwise, I'm going to have some orphaned email addresses laying around the database. So it keeps your data clean by using referential integrity. The relational database or traditional relational databases also, there's one other concept to be aware of, and that is this ACID concept, where traditional relational databases will ensure that anytime somebody is updating, deleting, or inserting data, that it's not stepping on actions that someone else is doing. So while I'm doing an insert, no one else should be able to do a select from that table until my insert is complete. And likewise, if I'm doing an update, nobody can do an insert. Or while I'm doing a delete, somebody could possibly do an insert, but while I'm doing a delete, somebody shouldn't be able to select or be able to update the record that I'm working with. So it has all these controls to make sure that you have the integrity of that database. It's not going to get corrupt. Non-relational databases throw all that stuff out. They say, we don't care about referential integrity. We don't care so much about the integrity of the data. I'll give you a perfect example of this. So if you have a bank, referential integrity and the integrity of that data is very important. If you discover that a couple of your transactions are missing from your bank account, that's going to be a major concern, and that could have pretty drastic ramifications for a bank. Now, take Facebook, for example. If a couple of your posts are missing over the period of a year, you're probably not even going to notice that they go missing. You're probably never going to notice that some photograph you updated or uploaded of your dinner from 5 weeks ago is not on Facebook. You're never going to know. You're never going to care. And in those limited times when you do care, it's not the end of the world. Their end user agreements certainly codify that expectation. So that's basically what they talk about in NoSQL, is that second option, that kind of Facebook world where we throw away that integrity in exchange for high performance. Now, why do they talk about this in the book? I think the reason they're talking about this is because they want to stress that newer technologies and frameworks represent new vectors of attack or new surface areas of attack. So we want to make sure that we're always prepared and thinking about these new technologies. And NoSQL certainly has its own vector of attack, and the thing about NoSQL is that it might have different syntax. So a typical SQL injection maybe won't work on NoSQL, but some new injection attack that we never thought of might work, or some syntax that we haven't tested against because we're just not familiar with that. So you want to bear those types of things in mind. You can't just say, well, I know that a SQL injection attack is a possible avenue of attack, so I'm going to test for SQL injection, but they're using some new technology on a web application that doesn't even use SQL. You have to think about some other way to test that and make sure that you test the other possibilities. So, and of course, we work in IT. In this world of IT, things are always moving very fast, so we always have to be prepared for this, for all this changing technology. So I think that's the lesson to take away when your book talks about NoSQL versus SQL. Finally, validation. So form validation, in your textbook, they talk about how form validation can occur either client-side or server-side. So when we talk about client-side validation, it's usually done using something like JavaScript if it's a web-based application. For client-side applications, it could be a Java applet, it could be a thin client or even a thick client, something on the client side, some code running on the client side. And then you usually have some kind of server-side validation, which is done using server-side scripting. So server-side scripting languages, examples of those would be PHP, ASP.NET, Java, Ruby, Node.js, et cetera, et cetera, et cetera. So all these crazy, and there's many more different server-side like Cold Fusion and things like that. The point is, you've got basically two sides of the equation. You've got the client side, which is where the user is, and you've got the server side where you're going to process that data. And that's the important distinction here. One is under the control of the user, and the second is not under control of the user. It's on the server side. So what we basically want to bear in mind is that form validation on the client side, while it's nice to have that form validation on the client side, you can't trust it. Now, there's a time and a place for client-side validation. So, for example, if your user, I've used this example earlier in this lecture, we talked about a state. If the user is putting in the state that they live in, if they put in NA, there is no state in the United States with the initials NA, so it would be nice to tell the user right away that, hey, there is no valid state NA. You have to put a valid state in. And maybe the user didn't know that that's what you're looking for, so it helps them. It's all about usability on the client side. You're helping the user put in the correct information, but you would not want to rely on that on the server side because my user's side could be under the control of the attacker. And if it's under the control of the attacker, they may be trying to use those input values to do an injection attack. So if I'm checking for SQL injection on the client side and the attacker knows that, they could just bypass those controls on the client side because they have control of their client side, and they could submit the data unadulterated from their side to do to carry out their attack. So basically, all form validation should be done on the server side. So that's the important takeaway from that section of the book, is that you should always do your form validation on the server side, and that's whether it's a web service or an API where the client is another application, or it's just a traditional form on a web page, or it can be an old-fashioned application that's running with a thick client or a thin client or a Java applet, even ActiveX controls, all that stuff. We don't want to trust it on the client side. We want to make sure we do that validation on the server side with whatever mechanism we're using on the server side. And we'll talk more about alternative environments later on, which has a whole other set of concerns with client versus server side validation stuff. So we'll talk about that later on. So that concludes the first part of this unit. In the next part of this unit, we're also going to talk about mobile applications and mobile devices. So stay tuned. There is another lecture video that you'll see for mobile devices. So keep an eye out for that. And if you have any questions, please let me know.